Hello and welcome back to this part 2 of the e-learning on the topic of spectroscopy from Q-Interline. If you didn't see video number 1, I encourage you to do so now, or you're invited to simply hang around. Hang on, here it goes with NIR in part 2. So people talk about NIR, they may talk about NIT, NearInfrared spectroscopy. The child has many names. But the conclusive thing is that we are working with the energetic upper part of the infrared, where we just learned in video number 1 that we had the visible light over here. This is the near-infrared region. If we blow that up, we are working from roughly 4,000 centimeter 1 to roughly 12,000 centimeter minus 1. People will say we only have the visible region starting a tad later. Yeah, but it's borderland. See, the good thing about near-infrared is that we have no longer the fundamental vibrations. We are looking at overtones and combination bands. That's a weaker type of spectroscopy, but that we can turn around to an advantage. Let's look a bit further into that. The spectroscopy in NIR follows basically the same rules. That means we still have our good old friend e to the minus alpha LC. We just have a little lambda there, and this extinction coefficient runs very thin when we get to the near-infrared. Hence, in order to get a reasonable absorption, what we do is, since the concentration is the same, we can simply work with much longer practical distances. The absorption in NIR is typically 1, 2, 3, 500 times lower than in the mid-infrared, but that, on the other hand, means that we can take the length, how much material we can shine light through, and go up hundreds of times. That becomes very, very practical, and I'll show you that in just a short moment. Another thing which is very elegant with NIR is that water doesn't absorb as much as in the mid-infrared where it absorbs a lot. And to get a feeling for these L things, the mid-infrared is typically dealing with layers of 5, 10, 20, 30, 40 microns, but then it's very thick. So it's not very practical, but you get beautiful spectra. The near-infrared means we are working with millimeter or centimeter path, much more practical. The near-infrared region offers us a few other advantages, and they become evidently important. One of the things near-infrared, or NIR light, the near-infrared region, it travels in glass. Whereas in the mid-infrared, we cannot have real glass like normal glass. We have to work with salts. A real salt like potassium chloride could be a window, but that's very not so practical because they are soluble in water. So NIR can work with normal glass. That means we can create optical fibers and take the light in an optical fiber a long way in the process, or we can simply work with glass petri dishes. These are some of the practical aspects of NIR. Further, we have much brighter sources, so it's easier to make a very, very bright near-infrared source than it is to do it in the mid-infrared. We have much, much higher sensitivity detectors available, and all these things combined makes NIR very, very useful for QC, daily operations, whereas the mid-infrared is typically used where you can spend half an hour getting one spectrum, but then you are rewarded with more knowledge on the molecules at hand, in what specific state they are. Where in the QC, we just want to know, does this sample contain 10, 10.5, 11% of that. Two different questions, two different techniques. Quite fair. That said, it's also quite relevant to state that infrared and near-infrared are all bound by the same math. It's basically just a matter of accepting that the extinction coefficient here is quite broad. It goes all the way from, if we had here, then we would have 400, and it would even go further. But if we look at a classical spectrum here of isopropanol, I have taken here isopropanol and put it on an ATR crystal. That means we have traveled, I would estimate 10 micrometers through isopropanol. We see a beautiful fingerprint region. We see OH, we see CH. And then right after 4,000, we see very, very small bumps. These small bumps will turn out to be the beginning of the NIR. But in order to study the NIR, we will have to create the path a lot because these peaks are so small. So now we put the isopropanol in an NIR cuvette and increase the path by a factor of 250. That means suddenly we have millimeters of path quite easy. And we see what happens is that these small noisy things, they rise to the occasion and becomes real peaks. We still have OH band, CH band, and the sorts, slightly broader, slightly less detailed to the naked eye, but if we do pre-processing of the spectra, we have exactly the same information. They are just weaker overtones of the fundamental vibrations. Zooming in on the near-infrared region, we have some major regions. In the fingerprint region, which is a word we do not use in the near-infrared, but still it's the longer wavelength region, we have a lot of details. It's still an OH, it's still a region of many, many different things. And then we have CH, OH regions throughout the spectrum. And we need to pay more attention to small shoulders, shapes of these peaks rather than individual peaks, because everything is smeared a little bit into larger peaks, broader peaks, and we have to resolve that with mathematics. We cannot resolve them optically, so no reason to crank up your spectrometer trying to resolve what has been smeared out by physics and pressure and a number of molecules. We merely have to take a low noise look at small shoulders and we can get very, very robust readings of our molecules. Okay, so how can we use near-infrared spectroscopy? Well, analyzers like the Quant, the Dericon Go, and Insight Pro are all based on NIR, which gives you an indication of the enormous amount of applications from at-line to online. Generally speaking, we can work in two modes in NIR, transmission and reflections. And these are used throughout our at-line and online. Some products are simply impossible to shine the light through, and some it's a lot easier or even advantageous to do so. We have to keep in mind that spectroscopy of this sort is kind of shallow. So the shorter wavelength, quite close to the visible, will penetrate 5 to 10 millimeters into the sample or even all the way through, where the longer wavelength near 4,000, 5,000 wave numbers, they will only penetrate like half or 1 millimeter. And in general, an NIR spectrum based on reflectance is the majority of the information stems from the surface. A good thing to bear in mind when you plan your sampling. Do not ask what's in the middle of the apple if you only look at the surface. So that concludes the little part 2 on the e-learning on spectroscopy from Q-Interline. In part 2, we looked at how NIR is related to infrared very tightly. We saw that there were certain advantages of working with NIR and some disadvantages. And I hope that by this introduction, you can better work with your spectroscopy and align some of the understanding to a better utilization of your spectrometer and your applications. At least I hope you had fun, and remember, awesome spectroscopy rocks. Thank you.